get back to the. Okay. Hello. Yep. I think that's good. Yeah, I mean, thanks for coming, and that we actually have water here. I will start from some introduction of myself. So the talk is about the AI fuzzing, and I'll quickly go through what is fuzzing and all these AI things. The major things is that it's not we are not applying from the perspective of really building a fuzzer rather than using the existing fuzzer. So that's the things that I will go across. And yeah, let's start with some introduction of myself. So I'm Andy, the founder of Mamori. So the whole Mamori is basically dedicating for building a automatic fuzzer for pen testing and the automatic value extraction. And my background basically I start from teaching in the academia that teaching in economics on optimization, applied econometric, and then moved to machine learning research. It's still in economics doing those kind of random forest classification, and I moved to the crypto on the AMM mechanism design. The major things why I'm here, that why we are here, that we care about security. Security is the bottleneck of making people why not coming into the crypto space. So the next thing is this talk is actually we do collaborate with University of Tokyo, and this is a working paper that I would like to present. And of course, the paper, a lot of extension. This is brief level of the idea that I want to talk about. Yeah, and yeah, first of all, fuzzing and AI. So should we fuzz everything, or should we just use AI, LLM to replace the whole security thing? So in the end, of course, the answer is mix of both. But how do we mix of both? For this talk is more about how do we use the AI to help the fuzzer. At the end of the talk, I will share just maybe my 2 cents of how a fuzzer can actually help AI on security as well. So before I actually understand what is fuzzing, we need to understand what kind of things result in the value extraction, the exploit. What is the nature of exploit? In the end, it's just functions and parameter. There's a sequence of function. You do add collateral, liquidate, remove, and then you run some input parameter. So functions and parameter equal to value extraction and take the money out. So this is the fundamental of why we are doing security pen testing. So what's the problem? Why? It seems quite easy, but what's the problem? How do we actually get into this kind of solution? The major problem is that for every single function, there's so many path that we can try first. That is this is amount out, amount in to data, and then all of these is actually having so many different revert path. Out of all these stochastic path, we need to find a way that actually result the target execution. So this is the major problem of a fuzzer, and then the major problem that we are encountering. So for instance, now, of course, we swap through front end, and then we have if I ask you that you need to input this parameter, how to do it? I mean, asking me, I also don't know how to do it. So that's the problem of why it's getting into a function, getting to the targeted branch is quite difficult. So how do then we actually understand deeper of why a fuzzer is not sufficient these days? It's because this is one of the hack that back in 2024 44 mil got hacked, and the first function that is about
create log campaign. Within this function, you can see these are the branch that we can actually get in. They have 538 branches. And out of these branches that we need to get into the valid branch, this is quite difficult. For a fuzzer, they usually just doing random mutation. They do by type, but still to get into the particular branch, it's just tough. So that is the stochastic nature. The next thing is about okay, am I good? I should be good. Yeah. The next thing is about the external call, and then in our smart contract system, comparing to traditional security, the major things that we have is that we interact with external call, so many different address, even single protocol. They would design their mechanism in a way that having so many different address. So last year we got the balancer hack. Balancer, they design in a way that the full contract, they will keep the money. They external call for their pool contract for the calculation. So in that sense, for the automatic fuzzing or automatic checking, we have to be able to identify the relationship between the core contract and then the callee external contract. This is another thing that is complexity. So it's the batch swap. They have talking so many different input parameter that we need to do, and then within the batch swap, we need to find what kind of input we should play around in order to
change the parameter for the external call, which is like another really sophistication that here. So the third thing is that is quite similar to the balancer case, but sometimes when we implement the smart contract, we take like really weird input parameter that, so among those kind of things is actually quite trivial. The difficult one is thinking about like the byte type call data. You need to construct a call data to call a function. This is crazy. And then this is like the things that a fuzzer or like a normal human or like the standard technique that is not really able to get into this kind of function call. It's just tough. Yeah. So so this is the batch swap similar that they have like the dynamic type, dynamic tuple, those kind of things is also like having messed up the storage log management as well. So then it's actually thinking about the solution. Then I try to present some solution, the proposed solution here. So we were talking about from stochastic inefficiency. So this is like the so many 500 branch, and then we can actually take out for the revert unrelated branch, and then we reduce the path that we have. So from that many to less. And all of these many, then how do we need to build a fuzzer to actually get into the path that what we want. So this is like from my thesis about like the stochastic chaos to directed precision, that we just need to get in a particular branch to yield some potential exploit. So this is like how do we do it? But how? Yeah, how do we do it? So the way that we design the mechanism is that we do like 3 layers. The first layer is actually thinking about the LLM, which is our core talk about here, that I will dive in each of it. The second layer is like using the fuzzer, the fundamental fuzzer, that basically building to get into the end of the branch. And then we also build something called basically GPU execution, the EVM execution on the GPU, but which is not about the talk here. So dive into the LLM component. So we have like the taint analysis, external call, complex data type, and more important is actually thinking about like the revert type. So when we actually do an execution, we encounter a revert, how do we actually use the LLM to guide us for the next step? So the first part is actually taint and taint analysis. It's quite a lot of people doing it. It's basically the static analyzer, try or build a sliver that back in time before the LLM, people used like static analyzer to know where is the vulnerability. So in the end, it's like some architecture that you play around and then you build chunking, semantic code segment for the LLM to understand better. For instance, like you can build a graph on the system architecture that like the core contract that is related to different maybe interface related to event, maybe to other item, to teach the LLM to understand the relationship across the contract. Because otherwise, like if we just plug in to the source code to the LLM, it's just tough to understand better. So this is like one of the things that we need. And when we actually thinking about the result, so this is like one of the very famous benchmark, the very liquid fold. And the things that what we are wanting to actually get is that we want to see the line of code, where is the problem, and then the potential problem. So make sure that here, I want to emphasize that I don't mind about like the false positive one, even though this may not be the critical, but because like we are applying some fuzzer. So after we identify the code region that we should investigate, we can use a fuzzer to investigate, to validate whether it's true or not. So that's why it's like having these to guide where we should go is a good way. Even if it's false or positive, we should still search it. Yeah, even if it's a suspected problem. The part B, let me see. The part B, yep, I'm good. So the part B is actually thinking about like the external call. The question to be asked is that the caller and callee relationship. So how do we manipulate the caller to get into change the external call relationship? So for instance, like there's a lot of things about price manipulation. The balancer case is actually an external call manipulation that you need to call from the full contract, which is like the caller will call that full contract, but like what they manipulate, they're actually manipulating the external call through the external call. So that's why it's like we need to link between the caller and callee concept. And how do we do it? Pretty much like we can also ask the LM to actually link it between these two. We just need to build a better call trace in the execution to know it. By understanding the call trace, then we can actually let the LM get the dependency graph between a caller and callee. Yeah. So basically, like there's like some approach that getting the caller function, getting callee function, and then link between like the address param, and then trying to generate some callee input for the LLM. Basically, we ask them to do this instruction, then they will suggest that
So this is like Uni v4 contract that the Bunny v2 got exploited, and then the v4 contract, the external call to the Bunny v2, then they would identify that like the caller contract is a swap function, and then what is the external call function is the before swap, but how do we manipulate it? They would suggest that where is the calling input to be able to get into the branch. Yep. The third things that we are thinking about is that like, we were talking about like call data type, those kind of like super weird type. We can actually like let the LLM to understand better. So Moon Hacker actually like is another case that got hacked. And as long as like the hack is that like, as long as you put a call data, that after you put the after they decode, ABI.decode, the whole call data to be M token, then the M token is the attacker address, then you get the validation. But the major blockage here is that the core data is just difficult to construct, to actually exploit. So we can actually ask the LM to reverse engineering that, because like understanding this logic, they are doing decoding. That means like, maybe we can do some encoding to reverse engineer the core data to actually like generate some potential searching opportunity. So this is like some other things. The final major things that we do it more dynamically to interact with a fuzzer is that the reward-based AI fuzzing. So this is like the whole engine that we can see that like the fuzzing engine that they are doing execution, then when we do the LUVM execution, they encounter revert. And for the revert, we need to see the whole execution trace, and then we convert this execution trace to let the LM understand that, where do we have the revert problem? And once we know the revert problem, we can actually ask the LM to do the part B and C or suggest for better result. Because like I know this is the revert message. Maybe they're talking about, your balance is insufficient. Your balance is have to be greater than 100. Greater than amount of input. Of course, like we know it as a human, but for a fuzzer or like a program analysis, it's just tough. So that's why it's like for the semantic things, we can actually pass it to the LM to do so. So one thing that like I encountered back in time, like I was like getting the execution trace. Then if we actually like getting the raw trace from the LUVM or using the Enfield debug trace, that we will get something like this, that they will tell you the stack, they will tell you the opcode and the program counter, all these things. Yeah, this is like not a chance. I don't even understand it. How the LLM understand it? The LLM don't understand it this way. So what we need to do is actually convert that call trace into some more semantic trace that having that we have like the def on this contract, and then the call on this, and then the whole call trace logic to let the LLM understand better what happened. And once we have it, we can actually ask the LLM to generate, what is the error message. We see the error message here, and then because of the error message, they will suggest what to do next. So this is like basically the whole from revert, and then like we query the whole engine, because like the fuzzing process, it doesn't work. We call the revert, we let the LM to actually help us to go to the next phase. One interesting thing is that what we implement is that like after the revert, sometimes it's not about your parameter input is wrong, because like sometimes it's about you haven't called some other functions first. So they may actually able to understand that, so for instance, like this is a swap function. If I directly call a Uniswap v4 bunny hook v2 or external call bunny hook v2 function, that swap function, they will actually need to call some other function first. So you may have to initialize the contract. You need to modify the liquidity to actually do something first. So that's why it's like the LM can able to suggest these kind of things, to help the fuzzer. So in the end, it's just like how do we get into end of the branch, and then the fuzzer itself, like how do we do it? Do we really understand the S-low, S-store operation to understand like each. This is like our control flow graph. Yeah, I never mentioned. This is like the whole control flow graph. And then for the basic block, we need to get into some particular opcode. We understand the jump I, and then we understand the jump I operation to get into a deeper branch. So this is like, I think the time is quite good. And so basically I will slow down a little bit. The discussion today, I talk about like what's the problem of the challenge of the fuzzer, and then how the AI actually can help. And I was talking about different components that we can help. And the major things that I want to like just quickly share about it is that how the fuzzer can actually help AI. We were talking about like AI is like is really involving for security. But how do we use the fuzzer to help the AI? In the end, what I see a fuzzer or like AI that they are lacking is actually these three things that a lot of people emphasize about data, but I personally think data is like it's important, but like comparing to the context that we should give the prompt and then the context, that is like the most important one. We also need to use the tooling. Now it's like we are entering in an era of like the agentic era, which is having reasoning instead of pure one-shot engineering. So we need to give them the tool to have the reasoning, collect the information. You can see like the agent, they may grab it, they may call different tool, get the information, and that help the AI to actually do it. So yeah, I mean, I hopefully should be good on time. And yeah, I think thank you very much. May the first be with you.
Right now, we can take some questions. Does anybody have?
Oh, I'm in 15 minutes. I'm on time.
Yeah, you are on time. We have 5 minutes left.
I thought I taught a lot.
No, you are good.
Yeah.
So thank you.
Yeah, thank you. Yeah, I talk really fast. Thank you. Yeah, I should go slower. Thank you.
No.